In this screencast, I'd like to review the result of our video analysis for an object that's in free fall, something that's dropped and it's under the influence of only gravity. You can see the video where I did this analysis elsewhere, but once I got this video and I graphed, once I analyzed the video, I displayed a graph of the vertical position as a function of time. What is that? Do you suppose that's a line? Is it linear? Is it a parabola? Is it a 1 minus an exponential or something like that? Well, I graphed the vertical velocity as a function of time too, and it looked reasonably linear with a couple of data points that were a little bit different from linear. I highlighted the relevant region and did a linear fit and found that there was a pretty good linear fit. The correlation was 0.99. And so that is pretty darn linear. And the slope of this line was minus 9.6 meters per second per second. That was the acceleration, the rate of change of the velocity. And indeed, I believe towards the end of class I had mentioned that yes, the acceleration due to Earth's gravitational field of any object, regardless of its mass, is 9.8 meters per second squared, and the direction of the acceleration is downward towards the center of the Earth. The value g has the numerical value, the variable g has the numerical value 9.8 meters per second per second. That's the acceleration due to gravity, also known as the local gravitational field strength. You can approximate g as 10 meters per second squared instead of 9.8 everywhere except for WebAssign. You can approximate it as 10 on quizzes and tests in the class and also on the AP itself. Don't make the mistake of referring to g as having a negative value. It is true that sometimes the acceleration due to gravity is down, and sometimes we call that the negative direction, but just as pi is always a positive number, g is always a positive number. Sometimes the answer to your question could be negative pi, but that would never mean that pi was equal to a negative number. Okay, this statement about Earth's gravitational field always giving a acceleration of 9.8 meters per second squared downward neglects air resistance. We will treat air resistance later. So I'd like to talk about this problem, which is very canonical, and physics teachers and the AP loves to ask you this to test your understanding of free fall. If I toss a squirrel straight up and I catch it at the same height, I'd like you to sketch a graph of the vertical position as a function of time, the vertical velocity as a function of time, and the vertical acceleration as a function of time. If you can, describe the final velocity, and I'd like to ask about what the nature of the acceleration is at the top of the flight, at the highest point reached by the squirrel. Well, here's the answer. Let's look at the velocity as a function of time graph first. The object is initially traveling upward in the direction that I have arbitrarily chosen to call positive at a large velocity, a large upward velocity that gets smaller and smaller until it instantaneously stops and changes direction. That occurs at this point where there's zero velocity, where the velocity shifts from positive upward to downward negative. And then it becomes slightly negative, and then more and more and more negative. If I look at the slope of that graph, the acceleration, look, is constant the whole time. And so there is this point at the top of the flight where there's zero velocity, zero vertical velocity, but there is still vertical acceleration because the velocity is still changing at that point. Graphically, there's still a slope of the velocity line at that point. And what shape does this velocity, if I'm looking at this velocity as a function of time graph and wondering what would the vertical position that corresponds to that be? Well, if it starts at some height above the ground, we would want a parabola such that it took this shape, where there's initially a large positive slope of the tangent line on that position function. Later to the point where at the top of the flight the slope is zero, the tangent line is horizontal, and then the tangent line becoming more and more negatively sloped as time goes on. So you can also say by symmetry that if you catch it at the same height that you release it from, the final velocity is going to be the opposite of the initial velocity. And you can make an appeal to symmetry, actually, to do that. You could prove it mathematically, but if you were to just say, by symmetry, the final velocity is the same as the initial, then I would find that convincing. That would be okay. Note that the acceleration at the top of the flight is minus, I guess it's downward. Acceleration is always downward in here. That happens to be what we call the negative direction. Minus 9.8 meters per second squared. It's very tempting to see the zero velocity and say, oh, there must be zero acceleration. But there is an acceleration. It's g, downward. Let's do this example problem. I drop a small moose out of a high window, and I want to ask what is its velocity after it's fallen for 3 seconds. First, I'm going to make a motion map in which I have a dot for the initial location, a dot for the final location, a bracket showing the displacement, which I label delta y because it's vertical. Delta x would be a horizontal displacement. I put velocity arrows where I can. Here, I see the word drop. Drop means release with zero velocity. It's not throwing something down, it's dropping it. Initially, there's zero velocity. So I write equals 0 for the initial velocity. There's my acceleration. It points downward. And in this problem, I am going to choose, you could make another choice if you wanted to call up positive and down negative. Then I list my values. The initial velocity is 0. The acceleration is negative because it is a downward acceleration, and downward is the negative direction, as I've chosen to call it. And its magnitude is 10 meters per second squared. We're interested in the velocity after 3 seconds, so delta t is 3 seconds, and what is the final velocity? Well, okay, now we'll find the one equation that directly links those 4 variables. v2 equals v1 plus a times delta t. Substitute the 0 value immediately. Solve algebraically for the desired variable. Here it's v2 and it's already solved for. Substitute with units, and there's the answer. After 3 seconds, there is a velocity of minus 30 meters per second. Let us briefly explore what would happen if we'd made the other choice. What if we'd called up positive and down negative? Now, the acceleration has a value of positive 10 meters per second. And I believe that's the only one of these values that changes. And so v2 is equal to a delta t as before. That's positive 30 meters per second. And so math has told us when we called downward positive that the final velocity is positive. That means downward. So no matter which way you call positive and which way you call negative, if you call down positive here, or if you call up positive as here, math tells you that the final velocity is down in both cases.